Hello, today we're going to be talking about properties of logarithms. So, if you're working through these notes, you should be seeing some exercises that come up, and as you come to these exercises, be sure that you work through them before you go on to the next page. So in this video, I'll be asking you to pause the video from time to time and work through the exercises before you go on to the next page. The solutions will be on the next page, but it's going to be a lot better if you try to work through these yourself and see how they work and try to work them out and see if you can actually do them, or see if you made some mistakes. If you make some mistakes, you'll learn from those mistakes and be able to correct them. Okay, so let's remember that the word logarithm means the same thing as the word power or the word exponent. So logarithms are actually just exponents in disguise. And so because of this, when we have a property of exponents, it's going to translate into a property of logarithms. And so what we're going to be doing in these notes is derive some of these properties, prove them, and then use them to algebraically manipulate certain expressions that contain some logarithms. Now, we also had a set of notes that we introduced the logarithm earlier, and we actually came up with not only logarithmic notation, but a few real basic properties there. And these are the most basic properties that we have there. And in fact, all of these are really equivalent to each other. If you get one of these, you get the others. And you could think of really any one of these really as kind of being the definition of the logarithm. We actually use the second one there as our definition of logarithmic notation. And so that says that if x equals b to the y power, then that's equivalent to saying y equals log base b of x. And so those are the same equation, one solved for x, one solved for y, just like y equals x plus 2 is the same equation as x equals y minus 2. And so those would be two different ways of saying the same thing. If you graph both of these for a particular base b, then they would be the same graph, the same table, the same set of points. Now, if you switch x and y on one of them, then you've got a pair of inverse relations, and that's what we have in the first line there, that f of x equals b to the x, and f inverse of x is log base b of x. Those are actually inverse functions of each other. So, of course, inverse functions undo each other. So if we have b to the power log base b of x, the same base there on both of those, so we take an x, we first apply the logarithm base b of that, and then we raise b to that power, to that logarithm, and they cancel out. The exponential and the logarithm cancel each other out, so that you're back to the x that you started with. Similarly, if we compose these functions in the opposite order, they also cancel out. So if we take x and raise it b to that x power, and then take log base b of that expression, log base b of b to the x, we're right back with the x we started with. So again, the b to the x and the log base b of x, they sort of cancel each other out when you do them in composition, do them in a series, a chain. Now, there are two special bases that we sometimes use for logarithms, and so we're going to have some special shorthand notation for them, and they're base 10 and base e logarithms. So if the base is invisible, you just see log of x and no base is visible, that base is base 10. You know, we always have all kinds of invisible things. If you just have x, then the invisible exponent is 1, and if we have, or the invisible denominator is 1. So the invisible base here is 10 if you see it, and that's called a common logarithm. Now, I put that into quotation marks, common. That's kind of my thing that I do a lot of times, because commonly logarithms used to be used very commonly to do calculations, okay, and to do very complicated things like taking certain roots, for example. We used logarithms to do those calculations back in the day before calculators. But now that we have calculators, calculators are commonly used to do most of these calculations, so common logarithms are not so common anymore. But they are still used in certain applications, and so we definitely need to know about those. And so if you see that, log of x, that's log base 10 of x. Natural logarithms are ln of x, L for logarithm, N for natural. So that's ln of x. and that's log base e of x. Remember we said e is the natural base, our standard base to use for exponential functions, and it also is our standard base to use for logarithmic functions as well. So we're going to use the ln of x mostly in this class as much as we can. One word of caution, sometimes you'll see in a computer programming language or maybe in a textbook somewhere where they write log of x and they mean log base e of x. That's unusual, but it could possibly happen, so just kind of watch out for that. But usually if you see log of x, and all the time in this course, if you see log of x, it's log base 10 of x. So let's see if we can apply some of our basic properties that we've done before, we've already seen here, to do these here. So we want to evaluate these and simplify these different basic expressions. They all involve either common or natural logarithms. So it's just applying our basic rules of logarithms, our basic defining rules that we saw in these in this box up here. Whoa. There we go, in that box, but along with knowing that the base is e or 10 as it's in that box. So actually see if you can work these out and come back when you're finished. Press pause now. Well, let's take a look at some of these here. Log of 100 is log base 10 of 10 squared, so that's just the power 2. The log base 10 and the 10 to the power cancel each other out, leaving only the power. Similarly, log of 0.01 is saying 10 to what power is 0.01, and the answer is -2. Log of 1 million is 6, because 1 million is 10 to the 6th, and when we have log base 10 of 10 to the 6th, they cancel each other out. So ln of e squared is log base e of e squared, so that's just, whoops, that's just 2. And ln of e to the x is x. E to the power ln of x is x. Ln of 1 is 0 because that's e to what power is 1? And the answer is e to the 0 is 1, so the answer to this is 0. Log of 1 is 0. In fact, log base anything of 1 will be 0. And finally, ln of e is 1. It's the power here on the inside, which is just 1. Now, what we want to do next is evaluate these following expressions. Now, two of these are going to be should be pretty easy for you. A and C are easy, but B is going to be probably a little hard. In fact, actually probably impossible to approximate this very well, but you should at least be able to get the whole number part and round it off to the not necessarily the nearest whole number, but find out what the whole number part is. And the decimal part is going to be more difficult. But see if you can go ahead and figure these two things out. Press pause now. Well, 4 is 2 squared, so log base 2 of 4 is log base 2 of 2 squared, which is the power 2. Log base 2 of 8 is log base 2 of 2 cubed, so the base and the power bases are the same there, and the exponential and logarithm, so they cancel each other out, leaving only the exponent 3. So, when I say log base 2 of 8, I'm saying 2 to what power is 8? The answer is 3. Log base 2 of 4 says 2 to what power is 4? The answer is 2. Well, 2 to what power is 6? Yikes. Okay, we don't know. It's not a nice natural number there, or even an integer, so that gets a little bit more complicated. But one thing we remember from our study of logarithms in general is these are nice, continuous, one-to-one functions. So there will be a correct answer here, and it is something between 2 and 3, because 6 is between 4 and 8, then log base 2 of 6 has to be between log base 2 of 4 and log base 2 of 8. So it's got to be between 2 and 3. So it's 2 point something. I don't know what to put in those question marks just yet. So we're going to have to figure out a way of doing this. So how are we going to figure out, a decimal? We have an approximation. It's 2, but that's not a very good approximation. Maybe it's, in fact, it might even be closer to 3. So it's somewhere between 2 and 3, but we haven't really narrowed it down much. Well, unfortunately, at least on the older operating system, a T84 or T83, you don't have a log base 2 button. But we do have buttons for base 10 and base e, the common and natural logarithms. In particular, we're going to make use of the ln button. So take your calculator and see if you can find out decimal approximations for ln of 4, ln of 6, and ln of 27, the natural log of 4, the natural logarithm of 6, and the natural log of 27. So we can just do that pretty straightforward with the calculator. It's pretty easy to do. Go ahead and get your calculator out. Try those now. Press pause and then come back when you're done. Well, here it is worked out. You just push the ln button and type in the number, close the parentheses, and enter, and there you go. And here they all are. You can see the calculator screen on the right, and I've just transferred it over on the left. Now, by the way, we could have actually come up with the whole number part of this, the units digit. If you remember, with a little bit of thought, let's see, e is around 2.72, or just a little bit under 3. So e squared will be a little bit under 3 squared, which is 9. So ln of 4, and since 4 and 6 are less than 9, okay, the output's going to be a little less. It's going to be less than 2, but of course 4 and 6 are both bigger than 2.72, so they're bigger than e. So it'll be somewhere between 1 and 2. So they're definitely 1 point something, which we see on the calculator. Notice the e cubed, since e is a little bit less than 3, e cubed will be a little bit under 3 cubed, which is 27. So we should see it will take a little bit bigger power than 3 to get e to that power up to 27. So the power is going to be a little bit above 3 when you do ln of 27. So 3 to the 3 point something should be 27, and we can see here it's about 3 to the 3.2958, etc. But of course, we don't really have to think that hard about it. All we got to do really is press this button on our calculator and get this to work out. Now, but what about something like, we still haven't gotten to be able to solve something like this, log base 2 of 6. We can do ln of 6, but not log base 2. Well, just as we can convert the formula for an exponential function from one base to another, we can also convert the formula for a logarithmic function from one base to another. And the key is a couple of things. We're going to derive this, and I'm going to give the statements and reasons for the proof here, but the expression that we're going to use is really mainly just two things. It's b to the n to the m power is b to the n times m. We're going to use that. And we're going to use this basic defining result about logarithms, that b to the power log base b of x is x. Okay, and then that and just one more little fact will get us what we need here. So here we go. We start with the statement that we know is true no matter what, x equals x. But we can rewrite x as b to the power log base b of x. See, on the left there, the b's, the b to the power and the log base b are inverses, so they cancel each other out, leaving the x. I can do the same thing on the right, but with a different base, a. Now, I'm going to rewrite b as a to the log base a of b. So a to the power log base a of b is just whatever's inside that little parentheses, which is b. So that's a different way to write that. Now, on the left, I have a to a power, and then the whole thing to another power. I can simplify or rewrite as a to the power, where I multiply those two powers. So I have a to the power log base a of b times log base b of x on the left. On the right, I've got a to the power log base a of x. Well, now I have two expressions with the same base. I basically have like a to the u equals a to the v. Well, we know that exponentials with the same base, that's a one-to-one function. So the only way you can get two things to have the same base, two things to be equal, and they have the same base when it's just a base and a power, the only way that can happen is if the powers are equal too. So we just let the two exponents be the same. Log base a of b times log base b of x equals log base a of x. And finally, I just divide both sides by log base a of b, and I get the expression that I have here. And what you see in the box here, this is our general formula for changing from a log base b to a log base a. So log base b of x is the same as log base a of x, except that we also have to divide by this factor log base a of b. Okay? Now, what base do you think we want to change to? Well, it needs to be something we have a button for, so we're either going to change to base 10 or base e, and I prefer e. It's a more natural base to use for us, so we're going to use base e. And so when you sort of replace a with e and use our simplified notation, this becomes log base b of x equals ln of x over ln of b. And so you can rewrite everything in terms of our natural base e. Just like we can rewrite our exponential functions, y equals b to the x, we can rewrite them as y equals e to the kx. So we can rewrite our exponentials in terms of a base of e. We can also write our logarithms in terms of a base e. Okay? Now, the only thing that's really hard about this is you might get it upside down. Here's a little rule, that just a memory trick that might help you. The b is lower here in the notation. It's already a subscript. It's lower than the x. So the b is lower than the x on the end. Just a little memory tool to help you remember that. Well, now we can apply this to say what's log base 2 of 6. That's what we were looking at earlier. We knew it was 2 point something. And actually, because that log base 2 is increasing concave down, we might have realized, well, it's going to be a little closer to 3 than it is to 2, but not a lot. And so here we get log of 6 divided by log of 2. That is natural logarithm of 6 divided by the natural logarithm of 2. ln of 6 divided by ln of 2. And then just type that in on the calculator, and we get this here. In fact, let me go ahead and type the calculator expression and put it in here as well. Okay. And so we have, just to see it, what you do, here's the ln button right here. ln of the 6. Now be sure you close this parentheses. If you don't, it's going to mess up. That's a common mistake people make with the calculator. Divide by ln of 2, close parentheses. So if you open in parentheses, you should close it. And that is the same expression that we had there. Okay? So, let you try some. Okay? Express each of these in terms of natural logarithms, which would be the exact way of doing it, and then approximate them to the limits of your calculator. So when I say this log base 2 of 6, exactly the best way you can say it really is ln of 6 over ln of 2. That's an exact value. That actually turns out to be an irrational number, so we can't make it into a decimal that either terminates or repeats, but we can approximate it to at least to however many digits our calculator has, and that's what we have on the right. So the right is an approximate, the number part there at the end, 2.584962501. That's a decimal approximation. Okay, the expression ln of 6 over ln of 2, that's an exact value. So on these down here in exercise 4, give me the exact value in with terms of ln's, natural logarithms, and then also give me a decimal approximation as far as your calculator will go. Go ahead and do this now. Press pause. Alright, so here we go. I've got it worked out. So log base 2 of 7 is ln of 7 over ln of 2. Log base 3 of 11 is ln of 11 over ln of 3. Okay. And you can see I've kind of got these. So here you see the calculator worked out. Here's the calculator part. So here you see ln of 7 over ln of 2 is 2.807, etc. Log base 3 of 11, ln of 11 over ln of 3. You can see, whoa, that one's a typo. I must have hit ln twice. Let's try that. Yeah, it should be somewhere between 11 is somewhere between 9 and 27, so the answer should be between 2 and 3. Should be 2 point something. Let's see if I can fix that screen. Alright, so we want, let me go ahead and do the whole screen. ln of 7 divided by ln of 2. This should be ln of 11 divided by ln of 3. And then ln 19 divided by ln of 8. And that should replace that screen there. Okay, so that means I've got to, so this should be 2 point something. Let's see, 2.182658339. Okay, so as far as my calculator will go, that's what we get there. And then the last one, let's see, this one, 19 over 8, I got that one, looks good. And then this one is ln of 8,268 divided by ln of 2, which I have here. And oh, I copied the wrong one. Okay, so let's fix that one as well. 13.01332267. There we go. Okay, now we got those correct. So how would I get a graph of log base 2 of x? Okay, so figure out how you would put this into your graphing calculator. So use your change of base formula to rewrite it as a way that you can put in your calculator using natural logarithms, and then actually put it in your calculator and get the graphs of these four things. See if you can go ahead and do that now. Press pause. Well, you want to rewrite them as natural logs. So log base 2 of x is ln of x over ln of 2. Log base 3 of x is ln of x over ln of 3. Log base 8 of x is ln of x over ln of 8. And log base 1/2 of x is ln of x over ln of 1/2. And so there we go. That's how you put them in your calculator there. I picked some kind of window. This is actually a square window. I went from like I think I went from like negative 5 to 25 and negative 10 to 10, and then put a zoom square. I think is what I did to get this window. So this will be a square window. The one that's coming decreasing concave up, that's the base that's less than 1. All the ones with bases bigger than 1 are very similar there. The one on the top, let's see, the bigger the base, the higher it's going to be. Okay. So for example, this one down here, log base 8 of x, you have to go out to 8 to get up to 1. Whereas the one here, you only have to, log base 3 of x, you only have to go up to 3 to get up to 1, and this one is, you only have to go out to 2 to get 1. And this one you go out to 1/2, and it puts you up at 1. So that's the one, and that's going down. Now, because logarithms are just exponents, although you might say, well, they're well disguised, but they are just exponents in disguise, the properties of exponents translate directly to properties of logarithms. For example, what does it mean when we say b to the n times b to the m equals b to the n plus m? Okay, let me rephrase that. If we multiply two things together with the same base, we keep the same base and we add the exponents. Let me rephrase it. The exponent on the product, when we're multiplying these two things at the same base, so as long as the base is the same, the exponent on the product is the sum of the two original exponents. Let me say it again. The power on the product is the sum of the two powers. Let me say it again. The logarithm on the product is the sum of the two logarithms. The logarithm, n plus m, is the sum of the two original logarithms, n and m. So the logarithm of the product is the sum of the logarithms, and that's exactly what this says in this box right here. Log base b of x times y is log base b of x plus log base b of y. So these two expressions, this one down here in the box and this one up here, are the same thing. They're saying exactly the same thing. And if you'll see when we do the proof here, the only thing that we're going to use is this property up here of exponents, and then this definition, the property basically it says b to the power log base b of x is x, that inverse function property there. And that's really all we're going to use. Now we are going to use a substitution to make the proof a little bit easier to follow. So we're going to let u be log base b of x. Well, that means if you rewrite that as an exponential, that says b to the u power is x. And similarly, v is log base b of y, so b to the v power is y. Okay, so with that substitution in mind, let's keep going here. So log base b of x times y is log base b of, well, let's see, x is b times u and y is b times v. So this is a b to the v power. Let me say that again. X is b to the u power, y is b to the v power. So this x times y is b to the u times b to the v. So I made that substitution. Now I'm going to use my property of exponents that says if I have two bases here, I multiply them together, I keep the same base and add the exponents. So that becomes b to the u plus v power. But now I have log base b of b to some power. They cancel each other out and you're just left with the power u plus v. But wait a minute, what's u? It's log base b of x. And what's v? Log base b of y. So we get our result that we want. The log base b of xy is log base b of x plus log base b of y. Exactly what we have in the parentheses here, which is what we're trying to show. Okay? Now, in a similar way, we have a property that says b to the n divided by b to the n is b to the n minus m. So let me say this. If you're dividing two things with the same base, you keep the base and subtract the exponents, top exponent minus bottom exponent. Or another way to say this is the exponent on the quotient is the difference in the two original exponents. Let me say it again. The logarithm on the quotient is the difference of the two original logarithms. The logarithm here, n minus m, is the original logarithm n minus the original logarithm m. So it says a logarithm of a quotient, log base b of x over y, is the difference of the two logarithms. So again, this expression right here about exponents is saying exactly the same thing as this expression about logarithms. Logarithms are exponents after all. So log base b of x over y is log base b of x minus log base b of y. We're going to use the same substitution we did in the last problem, and in fact this proof is very, very similar. So we take log base b of x over y, it's log base b of b to the u over b to the v. B to the u over b to the v, we use that property of exponents that says that's b to the u minus v. But wait a minute, the b's, log base b of x and b to the power, they cancel out. The only thing left is the power, u minus v, but u is log base b of x, and v is log base b of y. And so the result is that we get this result here, which is what we were trying to prove. Now we're going to combine these statements together here. Take log base b of wx over yz. Well, think of the top as one thing, wx is one thing, and the denominator is one thing. Now we can apply the property we just did and said this is going to give us a difference of logarithms. Log of the top minus log of the bottom. So it's log base b of wx minus log base b of yz. Now we're going to use the other property that we had to turn a product into the sum of two logs. So log base b of wx is log base b of w plus log base b of x. Log base b of yz is log base b of y plus log base b of z. Now watch out, this minus is on the whole thing, so we need parentheses here. The first parentheses we can just drop, the second one we distribute. So we finally get this expression here. It says log base b of wx over yz is log base b of w plus log base b of x minus log base b of y minus log base b of z. So now what I really want is actually something more general even than this. I want to be able to take any expression that's a fraction here, no matter how many things are multiplied together in the top and bottom, as long as it's all multiplication, we can break it down into individual logarithms with each factor getting its own logarithm. The factors that come from the numerator, from the top, those factors will have a plus 1 in front of them. And the ones that come from the bottom, like the y and the z, will have a minus 1 in front of them. and we're just adding those up with, or adding or subtracting them. We add the ones from the top, we subtract the ones from the bottom. Now, remember, all these properties of logarithms, or all the properties of exponents or radicals, those are equalities that are always true, so they can go forwards or backwards. So we can take something like the left-hand expression here, log base b of wx over yz, and expand it out. Okay, now we made it simpler in the sense that the things inside the logarithms are simpler, just a w or an x or yz, just a single variable. But we made it more complicated in the fact that we've got a whole bunch of logarithms rather than just one. We can also go the other direction. We can combine all the logarithms on the right into one single logarithm on the left. But to do this, all the coefficients must be 1 or negative 1 to use this property. It really doesn't matter how many of them we have added or subtracted, as long as the bases are all the same and the coefficients are either 1 or negative 1, we can combine them all into one single logarithm. Okay? That's what all that's saying. Okay, now, here's some examples. So log base 3 of 5 times x is log base 3 of 5 plus log base 3 of x. Log base 2 of 6xy. Now, just like we did this with when we were working with properties of exponents and radicals, we want to take the constants and factor them into prime numbers, prime factorization. So we're going to think of 6 as 2 times 3. Now when we do that, we can treat the 2 and the 3 and the x and the y exactly the same, and we can expand it as far as possible. So now we have our product of 4 things. There's no dividing, so all these will have a plus in front of them, but each one gets its own logarithm. Log base 2 of 2 plus log base 2 of 3 plus log base 2 of x plus log base 2 of y. Log base 2 of 2 is just 1, so I went ahead and simplified that for the final answer. The next one, log base 5 of 3x over 14y, I'm going to think of the 14 as 2 times 7. Again, everything is multiplied inside the parentheses there, except for the one big fraction, which is a divide. And so that means I can break this all into a whole bunch of logarithms. All of them are the same base as the original, log base 5. And every factor in the top gets a plus 1, every factor in the bottom gets a minus 1 in front of it. So we get log base 5 of 3 plus log base 5 of x minus log base 5 of 2 minus log base 5 of 7 minus log base 5 of y. Okay? So and we've expanded these as far as possible. We've made them simpler in the sense that it's the thing we're taking a logarithm of is a very simple expression, either just a prime number or a single variable. But we did get a whole bunch of logarithms that way. We can go as far as possible in the reverse direction if we'd rather. We want to combine these into a single logarithm. Now we made it more complicated because the thing inside the logarithm is a more complicated expression, where they're real simple on the left. But we made it simpler in the sense that we got down to one single logarithm rather than a bunch of little logarithms. So here we go. ln of x minus ln of y plus ln of 2 minus ln of 5. Can we combine them? Well, two things have to happen. They have to all be the same base. In this case, it's base e, so they are the same base. That's satisfied. And then the coefficients have to be either 1 or negative 1. And they are. So we can combine them into one single logarithm. Every one that's got a positive in front, that's going to be the x and the 2. That goes to the top, multiplied. So that's 2x. Then we multiply in the bottom all the factors, whichever ones of these terms are negative in front, that's going to go to the bottom. So the y and the 5 go to the bottom. So we end up with ln of 2x over 5y. The next one, notice they're all logarithm base 7. They all have coefficient 1 or negative 1. We can suck all that up together to one single logarithm, log base 7. And notice that the 3 is the only one with the positive coefficient, so it goes to the numerator. Everything else has a negative coefficient, so it goes to the bottom. So the 2 and the x and y are multiplied together for the denominator inside the logarithm there. Similarly, the last one is all log base 3, so we can put it together. Everything is, well, that's part of it. And then the other thing is that all the coefficients are 1 or negative 1. 3 of them have a coefficient positive 1, so those 3 go to the top. 2 times 5 times x. 2 times 5 is actually 10, so that's 10x for the top, and then the y goes to the bottom. Alright, now it's time for you to try some. Okay? Try this one here. So the idea is to expand them all the way out. So when we're done, we should get only logarithm of a single variable or a prime number. Expand that out as far as possible. When you get all these done, come back. Press pause now. Okay, well, you're back. Before we check that, I'm going to give you some more to do, the opposite direction. So take these four and do the opposite. Combine these so that you only get one single logarithm. Now the thing inside the logarithm may be more complicated this time, but you're only going to have one logarithm in the answer. So go ahead and combine these. When you finish these, come back and we'll check both of these problems. Press pause now. Alright, let's look at the first one. Remember, this is supposed to expand it out. Log base 2 of 5x is log base 2 of 5 plus log base 2 of x. Okay. 10xyz we can rewrite as 2 times 5 times xyz. So we want to do that first. And everyone's going to get its own logarithm. It's log base 2 of 2 plus log base 2 of 5 plus log base 2 of x plus log base 2 of y plus log base 2 of z. Log base 2 of 2 is 1, so that simplifies a bit. Next one, log base 5 of 2xy over 15z. Rewrite 15 as 3 times 5. Again, we can make a logarithm for each factor. Log base 5 of 2 plus log base 5 of x plus log base 5 of y. Those factors were in the numerator, so they got a plus 1 or positive coefficient. The rest of them are added. The rest of them are going to be subtracted, or in other words, have a negative 1 coefficient. Log base 5 of 3 minus log base 5 of 5 minus log base 5 of z. Log base 5 of 5 is 1, so we can simplify that one. The last one, we're going to rewrite 6 as 2 times 3 and 35 as 5 times 7. And, actually it's not the last one, but that is natural log of 2 plus natural log of 3 plus natural log of x minus natural log of 5 minus natural log of 7 minus natural log of y minus natural log of z. The last one, ln of w x over yz, is ln of w plus ln of x minus ln of y over ln of z, minus ln of z. The ones where we wanted to put them together, here they are. We have 4 of those. Notice that the first one, all of them are log base e, and they have coefficient 1 or negative 1. We can combine that. So we get ln of x times y divided by, let's see, 3 times 7 is 21. So it's x times y over 21, and then take ln of all of that. Oops, this next one should be log base 7. Okay, because it has to stay the same base. Okay, and they each one is all log base 7, so the answer's got to be log base 7, and the coefficients are all 1 or negative 1, so we can put it together. So the top's going to be 5 times 3 times x, which is 15x, and the bottom's going to be y. The next one, we're going to put them together, and they're all log base 3, so the answer's log base 3, and they're all 1 or negative 1, so we can put them together. So the top, you're going to have a 7, and the y are the positive ones, so that would be 7y. The 2 negative ones are the 90x, so that's 9x for the denominator. And you can see the last one is ln of wx over yz again. Now, it's easy to, I've seen students make up their own formulas, things that don't work. One that sometimes students will do that gets them confused, well, I'll just write it with ln. ln of x over y is ln of x minus ln of y. Well, that's correct. This says that the logarithm on a quotient is the difference of the logarithms. That's basically saying the same thing as this. Well, this is e. This is basically saying e to the n over e to the m is e to the n minus m. And basically, this is my n and this is my m. Okay. But some people get that confused by trying to say ln of x over ln of y, say, is ln of x over y. That doesn't work. Okay, that doesn't work. It also doesn't work this way. Sometimes they'll say this, ln of x over ln of y is ln x minus ln y. That one doesn't work. This one you should see doesn't work. Let a be ln of x and b is ln of y. We certainly don't think that subtraction and addition are the same. Subtraction and division are the same thing. A minus b and a divided by b, there's no way that's going to work out to be the same thing. So this is definitely bogus there, though that can't be true. This one's not true either. Okay, so when you get an expression with these on top of each other, really you can't do that. We could do a change of base formula. This is log base y of x, but other than switching to some base, which we'd really rather not do anyway, you're not going to be able to simplify an expression like that. Whereas this one does work. ln of x over y is ln of x minus ln of y. So you need to memorize these. Be sure you memorize them correctly. But you can also kind of sometimes use your calculator to do some checking for you. So, for example, if we were, or to check your memory, suppose we want to check log base b of x times y is log base b of x plus log base b of y. Well, we don't have all these letters on our calculator, but we could do it for a base e. If it works for base e, it's probably going to work for base b. So we could write this as ln of x y equals ln of x plus ln of y. We can put in some specific number for y, like y is 5. And then this becomes ln of x times 5, or 5x, is ln of x plus ln of 5. Well, let's see if that's actually true by checking it in a calculator. So you can let the left side be ln of 5x and the right side be ln of x plus ln of 5. And we check it for lots of x's by looking at our table and see that the tables match up perfectly. So we know that ln of 5x is ln of x plus ln of 5. And if that's true, then we feel pretty confident that we have memorized our property correctly. Okay? Now, we've got one more property that we're going to look at, and that is remembering this basic property here that says if you have b to the n and then raise it to the m power, that's b to the n times m power. Okay, a power to a power, you multiply the powers. Well, that translates actually here as this right here. Put a box around this. This property right here, which is what we're going to prove, that says if you have log base b of x to the n, it's n times log base b of x. It's going to come from this power property up here, and basically what you're doing is you're multiplying two powers. One power is n, the other power is the logarithm. Remember, logarithm is a power. So we're going to do a substitution this time. This time, instead of doing the two substitutions like the last proof, we're only going to need one substitution. So we're going to use the same one we did before. U is log base b of x, so that means b to the u is x. So log base b of x to the n becomes, the x can be replaced by b to the u. Now we can use our property of exponents there that says a power to a power, we multiply the powers. So that's b to the n times u inside there. But now we have log base b of b to some power. They cancel each other out, leaving only the power. N times u, but again, u, look back, is log base b of x. And so we have proved the property that we want there that says that if you take log of something to a power, it's the same as what you came up with. Well, it's the same. It's the n. The power can be brought out front, but when it comes out front, it's no longer power. It's multiplication. Or if it's outside multiplication, it can come inside, and then it becomes a power. Now, actually, it turns out there's a technical problem here. There can be a domain problem. If n is an even number, then if you plug in an x value here, you clearly are going to have an even function, a function that has y-axis symmetry, and it's going to be defined, well, you still can't take x to be 0, so it's not going to be defined at 0, but it is going to be defined for both positive and negative values of x, because once you raise it to the even power, then you have a positive, and you can do a log of a positive. On the other hand, on the right side, you can only evaluate it for positives, because if you put in a negative and take a log of that, it just doesn't exist. So we have a domain problem here when n is even. We can fix that by making the right one just reflect over the axis by putting absolute value there. Okay, so for example, let me show you a picture here real quick. If you say y equals log, let's just do ln of, let's say x squared, notice you get both sides there. But if you just did y equals 2 ln of x, you're only going to get the first quadrant, or the positive x part, first and fourth quadrants. But we can fix it to be exactly right by putting absolute value around the x, and now you notice that we get well, we get all of the whole graph, both pieces. Okay, now it's still undefined at x equals 0, but not for the other part. Let me go ahead and copy that. So this is let's go ahead and put the formula there too. This is f of x, or y, I'll just use y. Y equals ln of x squared, which actually equals 2 ln of the absolute value of x. And now we can see that graph there. So here's the basic rule then. You just bring it out straight away if n is odd, but if n is even, we need an absolute value. Well, this is maybe not too surprising, because remember in our properties of exponents we had this show up a couple of times where we had to have absolute value on the even case, and that shows up here as well. Okay. Now let's summarize. Okay, so summarizing here, we have basically three properties here. If x is positive, or if you limit to x is positive or to odd n, this last property just says if you got log base b of x to a power, you can bring the power out front. So here you use this when the base b and the x base, they're different. Okay, but if they're the same, you can use the middle property. Log base b of b to the x is just x. And then we use our property that says if we've got a bunch of things multiplied together, maybe with a division, in a logarithm, we can rewrite that as a whole bunch of different logarithms. Now we can go left to right or right to left on any of these. But we can just take just these properties in combination, we can simplify and manipulate some expressions. So let's look at some of those. Before I do that, let's summarize a few things here. So here's some properties of exponents and radicals. So again, property number 1 is really saying the same thing as property, let's see, I don't know if I can see them both at the same time or not. No. Property 1 is the same thing as property 23. Property 2 is the same thing as property 24. Property 23 and 24 put together makes 25. Okay? Alright, and then I did something here I shouldn't have done. I don't like to do this. Sometimes when you see things like this, they'll leave out the parentheses on the logarithms, and it actually is acceptable to do that, but I don't like it, because it really, you really should have the parentheses, because this is function notation. This is just like the f of x notation. Okay, and I think we need to emphasize that. So I'm going to go ahead and make sure that all of these actually have the parentheses that they should have around the input of the logarithm function there, the argument. Okay, and let's so let's just take a second to finish those up. I think I got them all. Okay, that looks better. Okay, and so those are your basic properties kind of all summarized together. And since they really are properties of exponents, the properties of logarithms, which are exponents, it makes sense to put all those together. And I've included our change of base formula, 29, our definition of E, 31, our definition basically of the logarithms, those four properties we started with, 19, 20, and 21. Oh, there's another one I missed. Right there. Okay. Alright, let's keep going. So that's just a one page you could print out summary. Now, we can combine these properties to do something like this. 7 log base 3 of x minus 5 log base 3 of y minus 2 log base 3 of 5. We'd like to combine these into one single logarithm. Well, we can't do it yet because the coefficients need to be 1 or negative 1. The bases all have to be the same as well, which we do have, but we don't have coefficients 1 or negative 1. So we first have to take care of that by bringing them inside the parentheses where they become exponents. So 7 log base 3 of x is log base 3 of 7. We bring the 5 in as a power and the 2 in as a power. I left the minuses out. You can do it that way. So now all the coefficients are 1 or negative 1, same base, we can pull them together in one logarithm. The one that has a positive, that x to the 7th, that's going to the top. Y to the 5th, and the 5 square goes to the bottom. 5 squared is 25. So we were able to put that together. Here I first distribute the 3 and get 3 ln of x minus 15 ln of y. And the rest is the same. Now I can bring the powers, the coefficients inside and make powers out of them. So this becomes x cubed, y to the 15th, 5 squared, and 2 cubed. Now they all have base e, same base. Coefficients 1 or negative 1, they can get sucked up into one single logarithm. The ones that are positive in the front are the x cubed and the 2 to the 3rd. So I get 2 to the 3rd x cubed in the top. And the denominator I get 5 squared and y to the 15th. 2 cubed is 8 and 5 squared is 25, so you see our final answer there. 1/2 of ln of the x is ln of x to the 1/2, which is ln of the square root of x. So rather than rewrite a particular, you might say, well, the ln of the nth root of x is 1 over n times ln of x, and think of that as a new property. You can do that if you'd like. But since we know how to make fraction exponents into radicals and back and forth, this is just combining what we already know. Alright, the next set of examples goes exactly backwards. We want to expand as far as possible. So again, we take the 4 and rewrite it in prime factorization form as 2 squared. Now we've got one logarithm of a bunch of stuff multiplied, so we can put this together. Now, by the way, if that had said 3 plus x cubed, we couldn't break that part of it apart. But since it's all multiplication, we can. So that's log of 3 plus log of x cubed minus log of 2 squared minus log of y to the 5th. I'm saying log where I mean natural logarithm. And then I can go a little further by taking the powers and bring them out front, outside, as a coefficient. And that's what I did on all these last 3. Now I can use, well, first of all, 6 is 2 times 3, and 25 is 5 squared, but then I also use the property that this is natural log of something to the 1/2. I can pull the 1/2 out front. Now it's 1/2 out front, so notice that I've got a parentheses around this whole expression here, so it's 1/2 times this whole mess. And then this part here I can break in 1, 2, 3, 4, 5 factors. I should have 5 logarithms. Log of 2, log of 3, log of x cubed, minus log of 5 squared, minus log of y to the fifth. And each one of these I can bring the powers out front as coefficients, which is what I've done there. Finally, I went ahead and distributed the 1/2 and expanded out as far as I could go. Alright, your turn. Expand these expressions into expression that has simpler logarithms. Expand as far as you possibly can here. Let's get it a little bit smaller so you can see all of them at once. Got 3 examples for you to do, 3 exercises. So go ahead and do this now. Work it out, come back and check your answers. They're like the examples we just did. Press pause now. Okay, now you're back. We're going to do the same thing, actually backwards. In this one, we want to combine each of these into a single logarithm. Okay, a single logarithm. Okay, go ahead and do that. Come back and check your answer in a minute. We'll check both of these exercises here when you come back. Press pause now. Alright, check 8 first. Right, 15 is 3 times 5, 8 is 2 cubed. Now we have it, a bunch of things multiplied together there, so we can break it into different logarithms. Log of 3 plus log of 5 plus log of x to the 7th plus log of z. Then the ones in the bottom have minus, so it's minus log of 2 cubed minus log of y cubed. And there's ln to begin with, so these are all ln's, in other words, log base e. Now, the only other thing we can do is the ones that have powers, we can bring the powers out front of the logarithm, and they become coefficients there, multiplied. So ln of x to the 7th is 7 ln of x, ln of 2 cubed is 3 ln of 2, and ln of y cubed is 3 ln of y. And by the way, that's the only one you have to kind of worry about. If that power is even, you need to leave an absolute value behind, but it was odd in these cases. Okay, so I'm going to rewrite all of this stuff here. Actually, there really should be, technically there should be another set of parentheses right there. That's your parentheses from your function. And then you have 6 is 2 times 3, 25 is 5 squared, and then that whole thing is to the 5th root, which is the 1/5 power. So that means I can bring so I've got log of some base to the 1/5 power. That's 1/5 times log of that base. So that's 1/5 log of that fraction. Now that fraction can be expanded out. It's 1/5 times the whole thing, so we got 1/5 parentheses on the outside. And then the inside we got log of 2, plus log of 3, plus log of 4, of x to the 4th, minus log of 5 squared, minus log of y to the 5th, minus log of z. And each one of those that has a power, we can bring it out front. Log of y to the 5th is 5 log of y. Log of 5 squared is log of the absolute value of 5, but absolute value of 5 is 5. Log of x to the 4th is 4 log of the absolute value of x. Okay. Even power, we needed the absolute value there. Next one, 12 is 2 squared times 3. The 3 on the outside can be brought out front. When it comes outside of the parentheses, it is now no longer an exponent, it is now a coefficient, multiplication. So it's 3 times that logarithm. That logarithm is broken into a bunch of others, so we need parentheses around that whole expression of 5 logs added and subtracted. That's log base 2 of 2 squared, log base 2 plus log base 2 of 3, plus log base 2 of x to the 5th, minus log base 2 of y to the 7th, minus log base 2 of z cubed. Log base 2 of 2 to the 2nd, they're the same base, so it just cancels out, leaving the exponent 2. But log base 2 of x to the 5th, the 2 and the x are not the same base, so the only thing we can do there is bring the 5 out front, where it becomes multiplication. The same way for y to the 7th, z cubed. And I went ahead and distributed the 3 then, in this case, and got the final answer. I decided not to distribute it the 1/2 and the 1/5 in the last case. Could be done either way. Alright, so now these go in the other direction, combining into a single logarithm. Well, we can't combine them until we get them to have coefficient 1 or negative 1. So we got to move these coefficients inside as powers. So this becomes log base 3 of x to the 5th, minus log base 3 of y cubed, minus log base 3 of 5 to the 4th. Now we can put it together. Coefficients are 1 or negative 1, all the same base logarithm. So we get a single logarithm with the same base, log base 3, of x to the 5th over 5 to the 4th y cubed. 5 to the 4th is 625, so there's our final answer. Alright, we got another one or two here. Alright, first thing I did is distribute the 2. 2 ln of 2 minus 10 ln of 3 minus 11 ln of x plus 13 ln of y. Can't put them together yet because we need to get the coefficients to be 1 or negative 1. So bring the coefficient inside the parentheses where it becomes a power. So that becomes ln of 2 squared minus ln of 3 to the 10th minus ln of x to the 11th plus ln of y to the 13th. Now we have coefficient 1 or negative 1, all the same base logarithm. We can make one logarithm same base, so it's ln, log base e. The positive ones are 2 to the 2nd and y to the 13th, that goes to the top, multiplied. And the negative ones are 3 to the 10th and x to the 11th, that goes to the bottom, multiplied in the bottom, in the denominator. And then we just simplify 2 to the 2nd is 4, and 3 to the 10th is 59,049. Yeah, I used a calculator on that one. Okay. And the next one, I can distribute the 1/2. You get 1/2 ln of x plus ln of y. That's ln of x to the 1/2 plus ln of y, which is ln of x to the 1/2 times y. You could also write that as ln of y times the square root of x if you'd like. So we have some algebraic skills that we've developed. Some for manipulating logarithms. They really are just our same skills for manipulating exponents that we already knew about, just kind of in a different form. But we do need to memorize those rules and learn how to apply them by practicing doing these expressions. And then one of the ways that we're going to use this is to help us solve equations that have exponential or logarithmic expressions in them. We're going to cover those techniques in our next section, and they'll be coming back to some of these skills that we're developing in this unit to be able to find exact solutions to those kinds of equations.